Hi, welcome back. Now let's talk about internet search engines, specifically the applications of Markov chains in internet search engines. So, of course, this is useful in the real world. In fact, the algorithm that we will talk about today, um, started from Google, and that's how they made their fortune. The one who designed this algorithm is Larry Page. He was the founder of Google. So yeah, let's first recall the most important part that we have learned from the previous lecture. Basically, it tells us that the value at time point k is simply equal to p raised to k times the value at time point 0. Here, p denotes the transition matrix. Now let's look at a first algorithm. Uh, in the book, it's called the Alice's algorithm. First, we pick any random page. Then we click any link that connects her to another page. We do it multiple times, track the number of times that each page was visited, and then calculate the fraction of visits. So what this means is, for example, if we have a web page here, we will randomly click links that will direct us to different websites. So the assumption here is that we are not able to, for example, go to any link. Let's, for example, Facebook. So that part is not factored in this algorithm. Okay, I'm sorry. All right. So here, the book recorded the number of visits to each page and the fraction of visits to each page. Here, we are assuming that at time point 0, we are 100% certain that she is at page number 2. All right. So this algorithm makes sense. Intuitively, it makes sense. But unfortunately, this is quite expensive to implement. Doing the choosing any random page, going to the link, etc. So for large N, this will be quite expensive to compute. But fortunately, as we can see, if we use Markov chain, we can simplify this algorithm. So first, let us introduce the notion of a graph. So basically, this graph is similar to what was provided in the book. This gives us, this gives us the model on how um, each page is related to um, each page. So how the pages are related. So some concepts here are from the field of graph theory. So I will try to do some quick introduction, or no, actually we will just try to explain how it relates to the web pages. So when we look at this graph, it essentially tells us that if there is an arrow pointing to a specific node, meaning that page is contained in another page, or there is a link to that page from a particular page. So for example, if we look at page number 2, since there are arrow going to 0, meaning there is a link in page 2 that when you click on it, you will go to page 0. Similarly, there is an arrow from 2 going to 5, meaning there is a link from into, so there is a link at page number 2 that when you click it, you will go to page number 5. And similarly, there is an arrow from 5 to 2, so meaning page 5 contains a link to page number 2. So a convenient way to describe a graph is by a transition, I'm sorry, an adjacency matrix. So as you can see here, 2, there's a 1 since 2 is connected to 0, and there's a 1 since 2 is connected to 3, and 2 is connected to 5. And as what we have seen earlier, since 5 is also connected to 2, there is a 1 in this entry. So yeah, again, the matrix below is just a representation of this directed graph. Okay, so far so good. Let us introduce some definition. So basically, it denotes the state vector x raised to k to be an n by 1 column vector whose ith entry is the probability that the surfer is on the ith page after k random mouse clicks. So here, for example, it tells us that we are 100% certain that at time point 0, we are at um, we are at page number 2. So for example, it could have been zero point 0.5 here, sorry, zero point 0.5 on the first row and then zero point 0.5 on the second column, to mean that there's a 50-50 chance that we are at page 0, and then we are at sorry, we are at page 1, and then we are at page 2. So you have to forgive me for this, since in programming, in the index starts at 0, so sometimes I might interchange page 0 to page 1, but I will try my best to be consistent. All right. So this is useful when we use it in conjunction with our adjacency matrix. So for example, if we multiply our adjacency matrix with our um, initial state, we will uh, get this array that sorry, we will get this vector with one on specific pages. But if we normalize that vector, we can view this as a probability. So basically, this tells us that there's a 30% chance, 33% chance that we are at page 0, 0, 1, 2, at page 3, and then at page 4. Later on, we will see the usefulness of this. Again, this is our adjacent adjacency matrix from above. Then we introduce another definition, the probability transition matrix. So basically, this probability transition matrix is computed from our adjacency matrix. Um, it normalizes its column so that each column can be thought of as probability. So to explain it better, let's look at an example. So let's try to compute the transition matrix for, I'm sorry, let's try to compute the probability transition matrix B using our adjacency matrix A. So here is the probability transition matrix. So since in column 1 there is only one non-zero entry, so we can see that it's still 1. But if we look at column 2, we have a 1 here, a 1 here, and a 1 here. The sum of this is 3. So basically we just multiply this column by the sum of this column. That's why, yeah, we multiply this column by the sum of this column. So 1/3 times 1 is 1/3, 1/3 times 1 is 1/3, etc. So as you can see here, similarly on the third column, there are 3 1s, so we expect the entries here to be 1/3 as well. On column 4, there are 2 1, so we expect the values here to be 0 0.5. And as you can see here, this is how NumPy um, this is how NumPy is displaying our probability transition matrix. So again, going back to our previous lecture, we have a transition matrix and we have a state vector. So we can easily compute what will be the value at any arbitrary time point using using what we have learned from the previous lecture. So again, this is the same function that I have provided on the previous lecture. So as we can see, if we use this, if for example we wanted to find out where we are after, let's say, 5 random clicks. Oops, sorry, I think I haven't. Yeah, I need to provide the initial matrix, which is x sub 0. I need to run this first. Okay. And then we need to pass the transition matrix, which is B. Alright. So basically this tells us that after 5 random clicks, there's a 12% chance that we are on page 0, 50% chance that we are on page 1, and 37% chance that we are on page 2. Again, indexes starts at 0, so I hope you're not getting confused by that. And finally, if we look at the state after 15 random clicks, this is now our um, probability. So as you can see, page 0, 1, 2, so around 27%. So meaning most of the time, after 15 random clicks, the fraction of times that we have visited page 2 is 27%, and it's similar to what the manual algorithm Alice has implemented. So again, the only difference is indexes start at 0 from the matrix that I have shown before. Sorry, here. So all right, and as you can see, we can still expect the same same properties that we have expected from previous lecture. So if we look at the state after let's say 20 clicks, I expect it to be still similar to what the value is at state 15. Oops, sorry. So it's different. So as we can see, after um okay, let me rerun the cell since I have another variable called b. Um, I have another matrix called b on the future cell, so that's why it's giving us a different result. I should have used another variable. I'm sorry. Okay, yeah. So as you can see, this is the value at state 15, and this is the value at state 20. The value looks, extremely similar to each other, and that's expected. Since what we have seen from the previous lecture, under some assumptions, this converges to a specific vector. Although there, again, like what I mentioned, there are some assumptions that I chose not to discuss, since I think it's not really important to the topic that we have at hand. And also, it's mentioned in the book that um, x raised to k is actually an eigenvector for the transition matrix B. I tried to implement it, but unfortunately, I think it's how Python computes the eigenvector. So yeah, I'm not getting the expected result. Um, yeah, I'm not getting the expected result here to be an eigenvector. Although the algorithm seems correct, since I tried to do the computation and it actually matches. So yeah, but again, it's not important in our discussion at hand. So to summarize, I think the main point of this discussion is this: once we have an adjacency matrix, we can compute a transition probability. Sorry, we can compute a probability transition matrix. Once we have a probability transition matrix, we can take any initial state, and using Markov, we can calculate what will be a future state. So that will be the TLDR for this discussion. Next, we have another algorithm, Bob's algorithm. So it's almost similar to the algorithm that we have seen earlier. It's just that um, it has a more realistic assumption. So it's assuming that we can go to another page that's not actually that's not actually in the page that we're in, meaning there's no link to the page that we're in. So going back to this example, Bob's algorithm considers the fact that once while we are looking at this web page, there's actually a probability that I will go to another website like Facebook, right? So yeah, there are some discussion that's listed here. So delta is a probability that he will choose a page that is linked to the current page, and choosing. I mean, um, as we know from probability, the complement of that is 1 minus delta, and then this comes from the fact that there are n pages. So there are some computation, some mathematics that was shown in this lecture, but the main thing that we will look at is we will consider is another matrix M. So basically, it's computed from matrix B from above. So from the probability transition matrix that we have seen before, and then we do this expression. So we have the delta, and then we have the 1 minus delta over n, as we have seen from above, and then it's multiplied to in. So yeah, let's actually look at some code to to make this concept more concrete, and let us compare Bob's algorithm versus Alice's algorithm. So let's consider a new graph. So I will create a new adjacency matrix. Again, this is the same adjacency matrix that we have from the book. So as we can see here, this is the graph. And as shown from the previous lecture, we can compute the probability transition matrix from the adjacency matrix from this code right here. So we have obtained the matrix B, and then doing the computation from above, taking that delta is equal to 0.85, we can actually um, perform the computation, and we will get this matrix M. So again, B and M here are both transition matrix. So there are just some, additional logic involved. So yeah, later I will do another summary to make my point clear. So again, here we are assuming, we are making a more plausible assumption here. We are assuming that the probability that you are on any of the six pages are equally likely. So yeah. So first, we compute the probability using the first algorithm, Alice's algorithm. So as we can see here, after 15 clicks, so the probability that you are on page 0 is 19%, and you are on the page 1 is 40%, on the third page you are 40%, and the rest are zeros. But if we use Bob's algorithm, we can see that no page has zero probability, since again Bob's algorithm actually take into account some other factors like going to a different page. So in reality, Bob's algorithm is more plausible to be get implemented in production. So to sum up this discussion, I wanted to highlight just a quick summary of what we have discussed. First, so the algorithm goes. So I will. So the two algorithm goes by this. If we use the Markov chain concept, first we have an adjacency matrix. Then from that adjacency matrix, we compute the probability transition matrix. And if we want to use the second algorithm from the probability transition matrix, we will do some computation given above, and we will obtain the matrix M, and then we will apply the same concept that we have learned from Markov chain from the previous lecture. So that sums up my presentation for Math 203. Let me know if you have any feedback or suggestions. Thank you and have a good day.